Worksheet 10C indeterminate beams. Determine reactions for the beam shown below using superposition and also assume elastic loading. So we have a beam with distributed load 5 kips per foot throughout the beams and 10 kips at point B, concentrated load. And we have fixed ends at A and roller at C. Use your engineering mechanics static knowledge at fixed support. In 2D, we have 3 unknowns. If you recall that here is AY, we have AX, and of course we also have moment, right? Moment reactions at the fixed support MA, and at the roller C we have CY. And how many equations you have, how many unknowns you have? As you can see, for here we have 3 equations, 3 equilibrium equation, Fx, Fy, and moment about at any point. And then we have 4 unknowns as shown there, which are Ax, Ay, Mx, Ma, and Cy. And with that, if you recall, we cannot solve with the number of equilibrium equation is not enough to solve the reaction, the external forces that we call statically indeterminate structure. Recall that one, so it will be statically indeterminate. Okay, and with that, that's why they call it indeterminate beams, basically. So how can we solve? We have to use the superposition in this case here. And how we apply the superposition? Several way that we can do. And in the solution in the PDF, you have 2 ways, but let's do one in that video here. So if I remove and know one of the reaction here without use the 3 equilibrium equation, then I can have that if I know one of the reaction and use the 3 equilibrium equation, then we can be able to find all of the 4 unknowns. So bottom line, if we can find one. So let me make that equivalent here. So from that, if that components, we can, what do we have in this scenarios? What do we have in that scenarios? Okay. So the scenarios here, if we have that remove, if I talking about CY, if we remove CY and consider CY at the load, right? Consider CY at the load, then the load there, this beam or this cantilever, it can become like this. Okay, the first scenarios I have and use superposition, the whole beam, and that it become a cantilever with the load it throughout of that, and that is 5 kips per foot for the total length is 8 feet, and then it equal to the cantilever of 6 feet with the extra 2 feet, something we did in worksheet 16B, and the concentrated load here 10 kips. Okay, So that is the load we have. And then cy, I remove cy, and become consider cy at external load. So let that one become the beam here, become a cantilever. A feet. And cy now consider external load. Okay, cy consider external load. So what do we have? If we have that scenarios, so with the 5 kip speed, the body will deflect down, and that deflection at one end 8 feet here, we call that is y1. And then the 10 kips at the location 6 feet from the fixed support, then this beam will be deflect and then continue to deflect with the another 2 feet, another 2 feet. So that one here, another 2 feet. So what do I have? I have the this is y2, the deflection of the cantilever 6 feet at the end, that is y2, and continue deflection with the something we did in worksheet 15b, that is theta, and the angle with that small deflection. So we have small angle, and we also have the relationship here for the additional deflection, that is y3. And for cy, with the load go up like that, then the deflection go up. And the deflection total here, I call that is y4. Okay, so that remove. So let write down here, consider cy at external load. So we have that. So what do we have in here? Can we find out y1? For sure. Can we find out y2? For sure. Can we find out y3? For sure. If you are not sure, go back to worksheet 15b. We do all of that. We did all of that. And then cy, can we find out? With respect to cy, that for sure. But as you can see, at C, ear roller. So you have to have the YC, the total deflection at C, have to be 0. What do we have? The total deflection at C have to be equal to 0. So what does that mean? On a total deflection here, we have y1 plus y2 plus y3 plus y4 have to be equal to 0. So whatever the deflection of on the external load going down have to be the same as the load cy, at if cy apply at C, going up have to be cancelled out, so that the roller still stay there, no deflection. That is the end condition we learned in class. So we have y1, y2, y3 equal 4. So that it become simple for now. As you can see, we can apply the finger here. So the first one, and so what do we have? 5 kips foot, y1 equal to what? Go back to this. We can apply exactly that finger 2 and the deflection negative WL4 over 8 EI. So the first one, and you can see it equal to negative WL, and in this case 8 feet 4 over 8 EI. Y2, it will be the same, but the L only 6 feet. So it will be negative W. Oh, not the W, the concentrated load. We have to go back here. It will be finger 1, and that is PL3 over 8 EI negative, as you can see there. So we can plug there. It will be P L cube over 3 EI, and here L is 6 feet, and you make that call when you plug the number in. And then the Y3 basically slope time 2 feet, because that similar to worksheet 6b that we already done. So go back here, the slope equal to negative PL square over 2 EI. So from that we can go back here, it's negative 2 feet time PL2 for 6 feet over 2 EI. And then CY consider the load at the end that we can use finger number 1 here, but the load is going up, so it becomes positive. Maximum deflection Y4 equal to negative PL3 over 3 EI. So go back here. P now is CY, so you can have it plus CY, and we have that is L in this case 8 feet, so L8 3 over 3 EI, and positive because that put up in there. So equals 0. The total deflection at point C have to be 0. So we can cancel out EI the same for all. So we can cancel that. So it's equivalent to W. So we can now plug in W is 5, L is 8, power 4 over 8, P 10 times 6 power 3 minus 2 cancel out, so we have P 10 times 6 cube over 1 and it cancel out, plus CY 8 cube over 3 EI cancel out equal to 0. And from that we can find out CY, one equation, one unknown. Wow, very marvelous. 21.3 keeps and positive going up, and that is the first answer. They asked us to find out the reaction, and we found out CY. And like I say, we use from the superposition and deflection, we already find out CY, and then we now we have 3 equations from equilibrium, and we already know CY. We only have 3 unknowns, AX, AY, and MA. And now we can be able to find out with the equilibrium equation. Okay, so that here, that is the first. And then we have the equilibrium equation. So we have 3, right? So the first one, as you can see, sum of all the force in x direction equal to 0. So that is here just only AX. So we have AX. So it means AX equal to 0, which is good. And then we have Y direction. So sum of all the force in Y direction equal to 0. What did we have here? it will be AY going up. And then we have 5 kips times 8, 40, negative 40. Then we have negative 10 for the concentrated load plus CY equals 0. And CY we already find out that equal to 21.3 kips. So from that we can have AY equal to 50 minus 21.3, so it will be 28.7 kips positive, send up our assumed direction of free body diagram going up. So that now it's nothing news to us. We learned that at statics long time ago, everyone, right? And then we take moment, sum up all the moment about the fixed support A, assume counterclockwise positive. So we have MA at the moment reaction at A, so we put MA. And then we have CY, and we have 5 kips, so 40 at the middle, so we have negative 40 times 4, and then negative 10 times 6, negative 10 times 6, plus CY times 8, and CY we already have 21.3 kips. So from that we can have MA equal to 49.4 foot kips. And that's what we done for this problem. And believe it or not, the process that we done here, we call compatibility when we consider CY at the external load. And compatibility is mean that deflection, in this case deformation, more specifically this problem reflection with our web. In this case that the roller deflection at roller C have to be 0. So that basically a compatibility that we are talking about. So with that we done for 16C, and I think you can be able to do the same for 16D.